Please clean the filter, yeah. The viewers at home can't see that, by the way, so they don't know what we're talking about. Okay, integration by substitution. It's the same concept throughout here. It's just we have to bring back everything about all the different types of derivatives and chain rule. Like we spent a long time on the chain rule. This kind of corresponds to the chain rule, if that helps as you work through this. Corresponds to working backwards with the chain rule. Chain rule. Okay, so we have to remember some derivatives that came up when you use the chain rule. On something like this, you could certainly expand it if you really wanted to, but it makes it a lot more complicated. If you know the chain rule, it's a lot quicker. Remember, this is, first of all, we're looking at finding derivatives here. Okay, later we're going to look at finding integrals, but can you try and write the derivative for that using the chain rule, and the derivative for that using the chain rule?
You guys are fast.
You guys are fast. That took milliseconds. The derivative of that, you need to just ignore what's in the middle, right? You're just looking at this as something. It doesn't matter. You're looking at it as something to the power of 20. Its derivative has to be 20 times something to the power of 19, but then you need to multiply it by the something, the derivative of the something inside there, right? 5. Okay, I'm not going to multiply this one out. Of course, you would make it, you'd make it 100. That to the, well, I guess we could write that over here because of what's in the brackets. 100 times 5x plus 3 to the 19th. The second one here, same thing, right? 20 times something to the 19th, but times the derivative of the inside there. And of course, you could do this and simplify. The last one here, again, 19, but times, what's the derivative of that inside function there? Cos x. You could maybe just leave it like that, who knows? Oops. Oh yeah, this is wrong up here. This is x squared plus 3, sorry. And this is sine x plus 3. Alright? You could reorganize it, probably put the cosine in front, but that doesn't matter. Integrating using the chain rule is called integration by substitution. Essentially what we're doing is we're working backwards from something that looks like the result of the chain rule. So this is key to understanding substitution. Instead of trying to memorize a million different questions, just understand what you're doing here. Integration by substitution is something you can use. You can't use it all the time. You can use it when what you are trying to integrate. So let's read this here. The function you are trying to integrate looks like the result of differentiating using the chain rule. So if it looks like the result of differentiating using the chain rule, you can use substitution. To make it simpler for yourself, you can use another variable. Just like you could have when you did the chain rule. We could have done the chain rule using a different variable. Like if we wanted to do this, we could just imagine it as d dx of u to the 20th, right? And said that u equals 5x plus 3. And then you could have done the derivative of u, the derivative of that whole function with respect to u, and then the derivative of u with respect to x, right? So we would have done derivative with respect to u of u to the 20th, and then times du dx, or u prime, whatever you want to call it. Eventually you got to the point where you could just look at this and do it without doing all that stuff. And eventually you'll be the same way with this, but for now we're probably going to substitute it. What we're probably going to do for this one is we're going to say, doesn't this look like the result of the chain rule?
It does. I think so.
It does. It does because what? Why does it look like this?
Because the brackets.
Let's hang on. Let's hear. Say that again. What? Oh, let's hang on. Okay. Okay.
1/2
I'm not sure I want to do this, but
X squared plus 1.
okay. You want to be Fernando? Can you answer that, please? What?
2x is the derivative of x squared plus 1.
So what are you saying? Circle what you're talking about here.
Okay, this is the derivative of this.
That's good. That's what you guys have to start to look for. Way to go, Fernando. As long as you can recognize that something is you have a function and you have its derivative there. Like if the inside function has its derivative on the outside, then you can use substitution. Like lower down, the question here is, can you use substitution on this? You won't be able to because you don't have the derivative of that inside function. So what we're going to do then is we're going to say this is the same as, we're going to use a u to represent x squared plus 1. So then we have the derivative of u to the 20th.
Do we have to use substituting?
For now, I think it's a good idea because you're going to get your du's and dx's and all this stuff mixed up. Because when you make this substitution here, we can't just change this dx into a du because they're not equivalent, right? Unless if u is equal to x, then we could make that direct change there. Du we could change to dx. If the thing we're integrating has got a u in it, this needs to be du for us to find the derivative. So what you have to do is use your substitution here to generate something that you can use to replace this du. What is the derivative here? If u is equal to x squared, du dx is equal to what? 2x. You can rearrange this because we're going to look at the du and the dx separately as sort of instantaneous change in each one. If du by dx is 2x, then du is equal to what? 2x dx. So what we're going to do is we're going to replace this 2x dx with du. Okay? So this whole thing becomes du. And then you can do the integral nicely because it lets you. So what is it? Remember, start with the power, don't start with a coefficient. It's u to the power of 21. And it's 1 over, divided by 21, 1 over 21, plus a constant. And then, of course, you have to put the u back in what it is because you started with x. So 1, what if we did? Then someone will...
I didn't change it to you.
Well, then as long as you're getting it right, there's always one. There's always one. So what is this? Well, no, we were doing the pseudonym, so nothing came to mind right away. So.
Yeah, that's what I got.
That is what you got. Must be right. So here's a confused calculus student. Actually, confused is not that. Confused is what, this? Okay, confused because
Question marks around.
That's scared though.
this is kind of just, I don't know.
I'm gonna cry in 20 seconds.
You want this is the other waste of time. No, but the reason that this calculus student is confused is because when we mentioned the chain rule, probably in their mind, even though they haven't ever said it out loud, the chain rule you have a nice function like this to the power of 20, whatever it was there, x squared plus 3. And when you find its derivative, you get 20 x squared plus 3 to the 19, but then what do you get on the end? Well, you get 2x, but you think of this as you get this extra part, right? This extra part appears when you're using the chain rule. You had this nice function that was just brackets there, and you're used to the coefficient in front, but then you get this extra part. When you're finding the derivative, this extra part appears, and so they get confused because they know that this is connected to the chain rule, but then they say, "Oh, wait a sec, what about this? There's this extra part here. Where did it go?" It went back inside. It went back inside because it makes sense that if the extra part appears when you're using the chain rule to find the derivative, yeah, it should disappear when you're working backwards, right? There's no extra part here. You see? No extra part. It's just this function here. Like the coefficient appears because it has to because there wasn't a coefficient in front there. But the extra part here disappears because you replace it with du. It disappears in this replacement here. That's a key thing to understand, and we must stop.